Let's talk about impulse momentum. Impulse, it's an E, momentum. All right, so this is an important concept, and in another presentation, I'll go through the concepts more. But in this presentation, I'm just going to derive the impulse momentum relationship. This all starts with Newton's second law, where we identify all the forces acting on an object and we understand that object's mass, acceleration of the center of mass. So the product of mass times acceleration equals the sum of all forces acting on the object. For simplicity's sake, I'm actually just going to deal with one force acting on an object, and I'm just going to write F equals ma to represent the mass of the object times the acceleration. Now, we know that acceleration is rate of change of velocity, delta v over delta t. It's how fast velocity is changing. What I'm going to do is substitute that into that equation into this equation here. So I get F equals m delta v over delta t. That's acceleration. And now I'm just going to do a little bit of algebra, and I'm going to multiply both sides of this equation times delta t. So I'm going to do delta t here, and I'm going to do delta t here. And I'm going to get this new equation, F delta t equals, well, I'll do it this way first, m delta v. And as long as the mass of the object stays constant, then I'm going to rewrite this as F delta t equals delta mv. And it's important that the mass is constant here, all right, and when I do this step. Situations where a mass would not be constant would be something like a rocket that's being blasted off, and that rocket is using fuel, and as the rocket goes up in the air, its mass is actually changing. And you have to account for that mass changing when you're trying to figure out the flight pattern of that rocket. But for all practical purposes, for the types of work that we do or what we're interested in looking at human performance, we are going to consider mass to be a constant. And what I get are these two parameters, which are directly derived from Newton's second law. So there's no magic here, all right? But I get a new parameter, F delta t, and we call that impulse. And what that means is that we are figuring out the magnitude of force and how long that force is being applied. And those two things together are impulse, okay? And over here, the mv part is a new parameter called momentum. It's got a terrible definition in that we typically just, if you look up in a physics dictionary or a physics textbook, momentum will just be described as the quantity of motion. It's still pretty vague, but it represents the product of mass and velocity. Okay. Now, in between this, these two words is this equality sign and that important delta delta symbol. I'm going to just write that here. Change. Okay. Impulse causes a change in momentum. Right. So we could rewrite this as F delta t equals mvf, final momentum, minus mvi. Now notice I did not put an f here or an I here for mass because we're going to consider mass to be constant. But I could put, now you can see where I could actually keep mass as not a constant and deal with that. But in any case, I have final momentum minus initial momentum. The mv is momentum. The delta mv is the change in momentum. And we have a change in momentum due to an impulse. All right, units. Let's look at units. Let me put units here. Units. For impulse, we have units of Newton seconds. Newton seconds. And for momentum, we have units of kilogram meters per second. Oh, those look different. but there's an equality sign here. They have to be the same. So let's do a quick unit analysis. Let me get another piece of paper here. Put that one off to the side, and let's do a unit analysis. And we have F delta T equals delta mv. I'll rewrite it that way. And our units are Newton seconds equals meters, kilogram meters per second. And they have to be the same because of the equality sign. Well, let's think back to what our base units of a Newton are. F equals ma. So a base unit of Newton is kilogram meters per second squared times that second there equals kilogram meters per second. And now hopefully you can see that this second in the numerator is going to cancel one of those seconds down here. And I'm left with kilogram meters per second equals kilogram meters per second. So everything agrees, which it should. But it's mostly correct to say impulse units are Newton seconds and momentum units are kilogram meters per second. That's the acceptable way. That's if you run into another biomechanist or you run into another physicist and you say, oh, I'm talking about impulse and my units are Newton seconds, and they're going to all understand you. If you do say impulse units are kilogram meters per second, technically you're still right. But we say impulse units are Newton seconds and momentum units are kilogram meters per second. They are the same exact set of units, okay? Now, what's also important is to recognize where we start to quantify impulse and also change in momentum. I'll get another piece of paper. And I'll do a force curve like this. And I'll put force on this axis, and I'll put time on this axis, and I'll make this in seconds. And let's just say that the force tracing does something like that. Not typical for a human movement, but that's okay. In this force tracing, we actually can visualize impulse as the area under that force tracing curve, okay? Impulse is the area under the force time curve. Okay, how do we get that? Well, how do we calculate area of, in this case, a rectangle? Well, area is length times, length times height, I'll do. So length times height. Well, what's our height? Our height is F, and our length is delta T. I wrote that backwards, but you can see that the product of those two, height and length, is F delta T, which you should automatically recognize as the equation for impulse. So when we do some work where we actually measure a force during some movement and we get something that looks maybe like that, I'll just do it like that, we can actually calculate the area under that curve. And if I continue this out and I do something else, like maybe this is a vertical ground reaction force and this is jumping, okay? It's pretty close. I get this tracing, I land on the ground, and then I trace, then I do another jump, but I don't jump as high. We can start to visualize the area under this curve is more than the area under this curve. So the impulse here is greater than the impulse in this section here. The change in momentum is greater due to this force tracing versus this force tracing. So momentum is greater, change in momentum can automatically be visualized by looking at the areas under these curves. And when we start looking at change in momentum, we're talking about kinematics, the change in velocity during a particular movement. All right. So when we start doing like a run ground reaction force analysis, we'll use this concept of calculating the area or visualizing the area under different portions of the curve to understand possibly what's happening with the movement. I have some other videos in a instrumentation class that I talk about how to calculate the area under a curve when it's not a simple rectangle. But for the purposes of this presentation, the most important thing is to recognize if you can visualize a bigger area under the curve, here versus here, you're visualizing also a bigger change in momentum. Okay, so that is the impulse momentum relationship. Thank you.